Hi everyone. In this video, we're going to talk about hypotheses tests in general, and then we're going to do some examples with the 1PropZ test. So this page gives an outline of how to conduct a hypothesis test. And I know that it's going to sound a little complicated at first, but we will do lots of examples of these. So the first step in conducting a hypothesis test is that we state the null and alternative hypotheses like we did on the previous pages. And then we're going to assume that the null hypothesis is true. So we want to assume that no change has occurred. We're going to then look at a sample, and we're going to see if this sample provides evidence against the null hypothesis. If it does, we're going to reject the null hypothesis. If it doesn't, then we fail to reject the null hypothesis. I know that that wording sounds really strange, especially with like the double negative there. But it's really important to understand that when we're doing a hypothesis test, we are not trying to prove that anything is true. We are just trying to see if we have evidence against the null hypothesis. To show or to prove that something's true is extremely difficult. You have to show that it's true in every scenario, in every case. But to show that something's false, you only need one counterexample to that statement. That one counterexample is proof against that statement, and you can then show that it's false. You have evidence that shows that it's false. So we simply want to know, is our example a counterexample, our sample a counterexample to the null hypothesis? And if it is a counterexample to the null hypothesis, then we're going to reject the null hypothesis and say that we have evidence for the alternative hypothesis. But if our sample is not a counterexample to the null hypothesis, then we fail to reject the null hypothesis. We're not saying the null is true. We're not showing it's true. We're just saying that we can't show that it's false. So how do we show that our sample is a counterexample to the null hypothesis? We look at the probability of observing that sample proportion or sample mean given that the null hypothesis is true. If the probability of observing this sample is really, really low, then we can say that this sample doesn't just exist because of normal variation in samples, that there is something else there, that we have evidence against this null hypothesis. So one of the examples that I've used, I don't know if example is the right word, but I'm just too tired to think of the other word. Metaphor, there we go. One of the metaphors I've used is that if you walk into a room and some people are 5'2" and some people are 5'7" and some people are 6'2", and that variation is natural and normal and you don't even think about it. But if you walked into a room with a group full of people and there was one person that was 9 feet tall, that would catch your attention and make you wonder why this height that's so different from the natural variation is there. I don't know, maybe that's a bad metaphor. The best way to study these is to look at a bunch of examples, so let's do that. We are going to look at two types of hypotheses tests. We're going to look at the 1PropZ test, and this is paired with the 1PropZ interval that you studied in chapter 13. The calculator command is 1PropZTest, and we're going to use p's when we talk about the population proportion. And the test statistic, which I know I haven't brought up yet, but the test statistic will be a z-score. And I'll explain it in the next example. A one sample t-test is the other type of hypothesis test that we're going to use, and this is paired with the one sample t-interval that you studied in Chapter 14. The calculator command is just t-test. We're going to be talking about means, so we're going to use mu. And just like with the t-interval, we're going to look at problems where we're given the sample mean and standard deviation, or where we have the sample data. The test statistic will be a t-score, and this is because, remember, with means, we were using the students' t models when we were looking at the intervals. So let's start with a 1PropZ test. It says a system manager at a large corporation believes that the percent of emails that are spam at their company is 80%. A random sample of 500 emails finds that 373 of them are spam. Does this sample provide evidence that the percent of emails that are spam is less than 80%? So let's first, before we start really solving this problem, make sure that we know what each of these numbers is. So this 80% is the accepted population proportion, right? This is the general belief that has been established, that 80% of these emails are spam. And then we have a random sample of 500 where 373 of them are spam. This is our sample. So we have a p-hat that is 373 out of 500. And if you were to do this division, you get a proportion of 0.746. So this is saying that if we have a sample proportion of 74.6%, is that different enough from the 80% to say that there's evidence that the population proportion is actually less than 80%? And I'm going to keep reiterating that there is a natural variation to p-hats. So we just want to know, are we seeing a p-hat that's just a natural normal variation, or are we seeing something that is exceptional? So looking at the hypotheses, remember the null hypothesis is that nothing has changed. We're using a p because we're studying proportions. We always use an equal sign for the null hypothesis. And the accepted is 80%. The question or the claim that's being made is, does this sample provide evidence that it's actually less than 80%? So we're going to run the test and report the test statistic and the p-value, and I'll show you how to do that. So we're going to go to the, we're going to use the stat button, and we're going to go to tests and choose the 1PropZTest. It's important to show me the command that you're using for your test, because there's a lot of test commands out there, along with the numbers that you're putting in for this test. So you're going to go to stat, arrow over to tests, and it's number 5, 1PropZTest. Right here, the first entry is the p sub 0. This is saying what is the proportion that is in your null hypothesis. Remember, any sub-zero is referring to the null hypothesis. The null hypothesis value is 0.8. Then it's asking for the sample. And this is the same x over n that was in the intervals. So this is 373 over 500. The next piece is asking us what symbol we're using for the alternative hypothesis. So we would say that our proportion is less than the null proportion. So just make sure you're using the exact same symbol that's in the alternative hypothesis. And then you're going to scroll down and hit calculate. When we calculate this, we're going to look for two pieces of information. The test statistic, which for proportions is a z-score. So it'll look like z equals, and a p-value, which is the probability of observing this sample given that 80% is the true proportion of spam emails. So when you hit calculate, it tells you the proportion symbol. Always make sure that you've used the right symbol. It's really easy to accidentally change this. I do it all the time. So just double check that that's going in the same direction as your alternative hypothesis. We have a z-score of negative 3.02. And remember back to when we learned about z-scores in Chapter 5. A z-score is the number of standard deviations from the mean. So if we're looking at the sampling distribution of samples of size 500, this particular sample is 3 standard deviations below the mean. That's really far. It's unusual to see a sample that is that far below the mean. So the probability of observing this sample is 0.0013. So our test statistic is here, that's the z, and this p right here, that's the p-value. And it's confusing, there's a lot of p's, right? The population proportion is a p, we have a p-hat, and now this also says p. And that's why I specifically write p-value. This p that they're showing in this output is the probability of observing this sample given that the true proportion is 80%. And this probability is really low, right? 0.13%. Because the probability of observing this sample is so low, then we say that this sample does not have this particular p-hat because of simple variation. And so we will then say that this is a counterexample to our null hypothesis, and we reject the null hypothesis. The biggest question that people say is, what is small enough to reject the null hypothesis? Right, so this one is pretty small, right? 0.13% is small. Everybody would agree to that. But where's the line? Is 1% small? Is 3% small? Is 10% small? How do we define a small probability? And that's where significance level comes in. So a significance level is that line. If it's below the significance level, then we consider it a small probability and we reject the null hypothesis. If it's above that significance level, then we say it's not small enough. It must just be due to variation, and we fail to reject the null hypothesis. The other term that we sometimes use for significance level is alpha level. And that's because we use the symbol alpha, this Greek letter, to denote the significance level. We have 4 common significance levels: 0.1, 10%, 0.05, 0.01, and 0.001. So 10%, 5%, 1%, and 0.1%. Somebody in my last class said 10% seems awfully high, and I would agree. Most people are not going to use 0.1 as an alpha level. But alpha equaling 0.05 is the standard right now for a significance level. So if no level is given or people are not really sure what level to choose, they'll always choose that 0.05. However, if you really want to make sure that you're correctly rejecting the null hypothesis, that you have correctly found a counterexample, you would want a lower alpha level or significance level. I interchange those terms. So a significance level of 1% or 0.1% is stronger, because if you can succeed with finding a counterexample with those smaller cutoff values, then you have better evidence. So again, if your p-value is below the alpha level, we reject the null hypothesis. And if your p-value is above the alpha level, we don't have a counterexample and we fail to reject the null hypothesis. Whenever our p-value is below the alpha level and we reject the null hypothesis, we say that our results are statistically significant. Okay, so looking at the exact same example that I had before, so I'm just kind of recapping that example where I have this p-value here. We're going to write a full conclusion using the significance level of alpha equal to 5%. So we want to start off with talking about whether or not we're going to reject the null or fail to reject the null and say why. So we're always going to start off this way. We're going to say, since the p-value is below 0.05, we reject the null hypothesis and conclude that there is enough evidence to suggest that the true proportion of spam emails at this company is less than 80%. All right, let me discuss what I just wrote. So I'm saying that since the probability of observing this sample is small, below our significance level, we reject the null hypothesis. I want to do something here. So since this is below 0.05, we reject the null hypothesis. And since we reject the null hypothesis, then we can conclude that we have evidence to support the alternative hypothesis. But when we write the alternative hypothesis, we use the context of the problem. So we're saying that we're going to conclude that that there is enough evidence to suggest. Notice I'm still kind of wishy-washy. I'm not saying anything's true. I'm just saying I have evidence that would suggest that the true proportion of these spam emails is actually less than 80%. So the next question is, well, how much less than? Right? You're saying that you have evidence that it's less than 80%. Does that mean it's 40%, 50%? What is then the true proportion of spam emails? And that's where the confidence interval comes in. So we want to find a 90% confidence interval and for the true proportion of spam emails. And we're going to look at how this supports our hypothesis test. One of the questions that I always get is why 90% and why not 95%? So I'm gonna answer that question now, but know that this is not ever something that's going to come up on an exam. I will always tell you the confidence level. You'll never have to figure it out. But so our alternative hypothesis was a less than, so we had a one-tailed hypothesis test with an alpha level of 5%. So that left tail was 5%, and a confidence interval is always the central percent. So if 5% is the lower percent, then I need another 5% to cover the upper tail, and I have 90% in the middle. I don't know if that makes any sense, but that's where the 90% is coming into. I'm not just choosing it out of thin air. It's related to this alpha level here and the fact that this is a one-tailed test. Okay, so I don't have a calculator picture of finding this this hypothesis test, this confidence interval, because we did this in chapter 13. But I hope you're following along with your own calculator, because what I want you to see is that when you go to do the confidence interval for this proportion, the information that you put in for the test is already automatically in for the interval. Your calculator is going to assume that you're going to find an interval next, and it's going to automatically populate the information. So when we find a confidence interval to support this test, we're going to find a 1PropZ interval, right? This was a 1PropZ test. So we're going to look at the 1PropZ interval. And that asks for an X, an N, and a C level. And again, the X and the N are probably already filled in for you. They already say 373 and 500 because you did the test already. The only thing you might have to change is the C level to 90%. And you're going to get a confidence interval of 0.71398 and 0.77802. So we would say that we are 90% confident that the true proportion of spam emails is between 71.4% and 77.8%. So notice that the interval gives us a range for where the true proportion is. The test showed that it was below 80%, and the interval shows that it's between 71.4% and 77.8%. So if you're ever asked, does this support the test conclusion? First of all, the answer should always be yes. Your interval should always, always, always support your test. And if it doesn't, then there's something wrong. But how do I support this? How does the interval support this test? The entire interval is below 80%. So it supports the alternative hypothesis, which we said we have evidence for, and rejects that 80%. 80% is nowhere in that interval. So we would say that this supports the hypothesis test because the entire interval is below 80%. So just a quick reminder that we have assumptions and conditions, and the assumptions and conditions for this 1PropZ test are the same as those that we had for the sampling distribution for proportions, as well as the 1PropZ interval. So we have this these core three that are always there, but when we talk about proportions, we talk about the success-failure condition, which is that the number of successes has to be greater than or equal to 10, and the number of failures have to be greater than or equal to 10. And just keep in mind that when you're checking this is taking the sample size times the true proportion, the population proportion, not the sample proportion. So sometimes that gets a little tricky. But most of the time we have a really large sample size, and this is met without any kind of issue. All right, let's do one more example of a proportion test. So just like when we did intervals, sometimes a proportion is given to us in counts, like it was in the last problem. We had 373 over 500. We were given the number of successes divided by the sample size. And sometimes the p-hat is given to us as a percent, and we have to then calculate that number of successes. So that's what we're going to see in this example here. This says a nationwide survey of working adults indicates that only 50% of them are satisfied with their jobs. The president of a large company believes that more than 50% of the employees at their company are satisfied with their jobs. To test this belief, a survey of a random sample of 120 employees is conducted. 54% of them report that they are satisfied with their jobs. Can this president conclude that more than 50% of employees at the company are satisfied with their jobs? Use an alpha level of 0.05. So first of all, what do we know? Which numbers go with which here? So this 50%, that's the nationwide true proportion. So that is the accepted proportion. Then we have a p-hat, a sample proportion of 54%, and a sample size of 120. So the question is this 54%, I mean, everybody knows 54% is above 50. So can this president just say, hey, I got a sample of 54%. That's more than 50, therefore more employees at my company are satisfied with their job? No, this person cannot say that. Nobody can say that. We don't know if this 54% is just sample variation, that normal sampling variation that we keep seeing, or is it exceptional enough to say, yep, there is a difference. So we need to conduct a hypothesis test. So we would say that the null hypothesis is that nothing has changed. The proportion is still 50%. And the alternative hypothesis is that the proportion is greater than this. We're going to run a 1PropZ test. The first thing it's going to ask us for is the null proportion, which is 50%. And then it's going to ask us for that x over n. Remember that in order to calculate this x, we have to take the sample proportion, the 0.54, and multiply it by the sample size. That gives us the count of people that said that they were satisfied with their jobs. So we would take 0.54 and multiply it by 120. And I think you get like 64.8. So we would round that to 65. And then the n is the sample size 120. So 65 out of 120 should give us that 54%. And then it's going to ask for the symbol. So we would say that our proportion is greater than the null. All right, let's look at it here. So again, we're going to tests, and we're going to do the 1PropZTest. And you can see here that we have that's a 0.5, and our count, our x, is 65 over 120, and we are using the greater than symbol, and then we're going to calculate. There is a draw feature here. I was going to look at it, but I might save that for future chapters. Right now, it's not really too important to look at that. I'll start it over. All right, so the true proportion, put in all the information, and remember that we are reporting the test statistic, which is the z-score. So this z-score is 0.913. That's less than 1 standard deviation above the mean. So if I look at the sampling distribution of all of the samples that are size 120, this one is less than 1 standard deviation above the mean. That's not that unusual. And so you can see that the p-value right here, the p-value, the probability that I observe this is 0.18. 18% is not small by any means, but it's definitely more than the alpha level. So we would say, since the p-value is greater than or above, doesn't matter which, above 0.05, we fail to reject the null hypothesis. And conclude that there is not enough evidence to suggest that the proportion, the true proportion of employees at this company that are satisfied with their job is more than 50%. It's a long conclusion, but I want to emphasize that the conclusion is the most important part. Understanding this conclusion is very important. The calculator is running the test for you. You have the hypotheses, the calculator's doing all the calculations. Being able to interpret what you are given is by far the most important thing to do. So we're saying that this sample is not a counterexample to what is accepted, which is the 50%. So we are, since this is above the alpha level, we are failing to reject the null hypothesis. And then we're concluding that there's not enough evidence to suggest that the alternative hypothesis is true. There's not enough evidence to suggest that the proportion of employees who are satisfied with their jobs is more than 50%. I have an error here. Oh my God, I wrote 54 there. That is really bad. This is 50, guys. I'm so sorry. wow, I can't believe I put a 54 there. I am so sorry. This is always your hypotheses are always the population proportions, and it's always the same. If I'm using 50% for the null hypothesis, I'm using 50% for the alternative hypothesis. I apologize. So we are saying that we don't have enough evidence that it's more than this 50%. All right, in the next videos, we're going to do the t-test.